Describing transformations. What is transformation? It refers to changes made to a point, a shape, a relation, or a set of relations to create a new point, a new shape, a new relation, or a new set of relations. Translations, reflections, rotations, and dilations, stretches and compressions are examples of transformations. The different types of transformations can be combined to produce a final image. First, let's look at translation. Translation refers to moving an object without changing its shape. We can have left-right translation, which is also called horizontal translation. We can have up-down translations, also called vertical translation. So now I have a cat, and I'm going to translate it to the right. As you can see, the shape of the cat didn't change. It just moved from one side to the other on the grid. I can also move the cat up. Okay, this is now called vertical translation. There's no change to the shape of the cat. It just moved. Rotation. Rotation refers to turning the original object around between 0 to 360 degrees. So I have a cat. If I turn it upside down, it is a rotation of approximately 180 degrees in this clockwise, and we can also do it counterclockwise. It doesn't change how the cat looks. I can have the cat, and I can turn it a little bit. Okay. Now, according to the arrow, this is a rotation of approximately 207 degrees clockwise. I can also do it counterclockwise, and then the angle will be different. Now, if I turn the cat a bit differently, this time I rotated it about 240 degrees clockwise. I can also look at it as turning the cat counterclockwise with a different angle. Now let's look at reflection. Reflection refers to a mirror image of the original object. We have left-right reflections, which means there is a reflection in the y-axis. We have up-down reflections, which means we're reflecting in the x-axis. And we can have diagonal reflections. For example, we can have a reflection in the line y equals to x. In this course, we will only look at reflections in the y-axis, x-axis, and the line y equals to x. So here's my cat again. If I reflect it in the y-axis, okay, then my cat did change a little bit. Okay, well, we can still tell it's a cat. Now, let's look at reflection in the x-axis. Okay, so now it looks upside down. Okay, and there's my x-axis. Now, if it's diagonal, so first this is the line y equals to x. And if I reflect the cat, okay, in this line, the image will change a lot. So the cat is reflected in the line y equals to x. Now, if I rotate this image a little bit, you will be able to see the reflection better. Okay, as you can see, the cat is a mirror image of itself. Next, we're going to look at stretch. Stretch refers to an elongation of the original object. We can have left-right stretches, so it's also called horizontal stretch. We can stretch something in the up-down direction, so that's called vertical stretch. So with my cat again, if we stretch it horizontally, then it looks longer. We can also stretch the cat vertically, like so. So these are called stretches. Compression. Compression refers to the shortening of an original object. So we can compress something in the left-right direction, so that's called horizontal compression. We can also compress something in the up-down direction, which is called vertical compression. So this cat again, we can compress it horizontally, and this is what it looks like. And we can compress the cat vertically, and this is what it looks like. So this is vertical compression. Vocabulary needed for transformation. Original point is a point from the original figure or graph. So in our previous examples, we can get original points from the picture of the cat. We call these points point A, point B, point C from the original picture. So after the transformation, we get image points. So an image point is a point that has been transformed from an original point. And we call these points A prime, B prime, C prime, etc. So the original point is called A. The image point would be called A prime. An original point is called B. The image point is called B prime, etc. So they share the same letter to show the transformation has occurred. So back to the example of my cat. So let's focus on its left eye. So let's say we focus on that one point and we transform the whole cat. But now we want to talk about the specific point of that left eye. So for the original point, that would be the point -3 and -3. After the transformation, then the image point is the point 5 and 0. So we have the original cat. The left eye is called A. And then we have the image cat. And the image point is called A prime. We're going to learn how to use mapping notation to describe transformations. When we describe in words, we say that we're transforming the original cat to the image cat. So we're using all the original points from one cat to produce all the image points in the second cat. In mapping notation, we would say the same thing using symbols. So for the original cat, we use a set of points generalized by x, y, and we say that it's mapped to all the points x prime, y prime to represent all the image points in the second cat. So the cat has moved 8 units to the right and 3 units up. In mapping notation, then we say that all the original points x, y, the x coordinates have moved 8 units to the right, and the y coordinates have moved 3 units up. So that's why we add 8 to x for the x coordinate, and we add 3 to y for the y coordinate. So if we look at one specific point example using the left eye, then we say that the left eye has moved 8 units to the right and 3 units up. So in mapping notation, we actually have numbers now. So the original point is -3 and -3, and then it's mapped to the point 5, 0. So when we check the map, -3 plus 8 gives us 5. And for the y coordinate, it's also -3, but this time we add 3 units up, so it's now a value of 0. When describing a set of transformations, this is the order we use. Reflection and or stretch or compression should go first. And then we would describe the translations. Why? Let's look at the mapping notation. When we write it in mapping notation, we have the set of original points, x, y. and it's mapped to the image points represented by kx plus d, ay plus c. If we look at kx plus d, k is multiplied to x and then added to d. When we look at ay plus c, we see that a is multiplied to y and then added to c. Now what's going on? K and a, they represent reflection in the stretch or compressions. D and C, they represent translations. So according to that math, we need to multiply a number to x before we can add other numbers to it. Similarly, we need to multiply a to y first before we can add c. So the reflection in or stretch or compression must be done first before we can do the translations. So it's part of the math language. K represents horizontal reflection in or stretch or compression. When k is greater than 0 and the absolute value of k is greater than 1, there is a horizontal stretch by a factor of absolute value of k. So if you look at the cats, okay, we have a transformation happening and it's a horizontal stretch. We can see that with our eyes. And because k is greater than 0, there's no reflection, so the cat is in the same orientation, okay, and same direction as before. Now, what is absolute value? Absolute value refers to when we analyze the number k, we only focus on the value of k and disregard the sign. So it doesn't matter if k is negative or positive. When we want the absolute value of k, we just pretend that k has a positive value and we only look at that positive value. So when we're analyzing the horizontal stretch, we just look at that number for k. And here we said k is greater than 1. Why does that number have to be 1 and not something else? Now let's go back to our mapping notation above. Look at kx plus d. K is multiplied to x, is multiplication. So if k is 1, then x doesn't change. Okay, 1 times x is still x. If k is greater than 1, for example, is 2, then 2 times x means x is doubled. So that's our stretch. So k has to be greater than 1, or I'm sorry, the absolute value of k has to be greater than 1 in order for us to have a stretch. When k is greater than 0 and the absolute value of k is less than 1, this means that k is between 0 and 1. There is a horizontal compression by a factor of the absolute value of k. So for example, if k is 1/3, okay, 1/3 is a number between 0 and 1, then we say there is a horizontal compression by a factor of 1/3. And 1/3 is multiplied by x, so then the number will become smaller. So that's our horizontal compression. Next, we want to look at when k is negative. So when k is less than 0 and the absolute value of k is greater than 1, there is a reflection in the y-axis, and we also have horizontal stretch by a factor of the absolute value of k. So as you can see in the picture, the cat is reflected and then it's also stretched horizontally. When k is less than 0 and the absolute value of k is less than 1, there is a reflection in the y-axis, and we also have horizontal compression by a factor of the absolute value of k. So you can see that the cat has been reflected and is also compressed. Now let's look at D. Okay, it represents horizontal translation or horizontal shift. When D is greater than 0, there is a horizontal translation absolute value of D units to the right. So when D is bigger than 0, the object is going to move to the right. When d is less than 0, which means d is negative, then the object is going to move to the left. And we say that there is a horizontal translation, and we use the absolute value of d because d is negative this time. And then the negative symbol is represented by the word left. If it's positive, it's right. If it's negative, it's left. Now let's look at the y-coordinate. A represents the vertical reflection and or stretch or compression, just like how K represents the horizontal reflection and or stretch or compression. K affects the x-coordinate and A affects the y-coordinate. So when A is greater than 0, the absolute value of A is greater than 1 as well, then we have a vertical stretch by a factor of the absolute value of A. So you can see that the cat is stretched vertically this time. So it's getting longer vertically. When A is greater than 0 and the absolute value of A is less than 1, there is a vertical compression by a factor of the absolute value of A. So the cat is squished vertically, so it's compressed. When A is negative, so when A is less than 0 and the absolute value of A is greater than 1, we have a reflection in the x-axis and a vertical stretch by a factor of the absolute value of A. When A is less than 0, the absolute value of A is less than 1. There is a reflection in the x-axis and also a vertical compression by a factor of the absolute value of A. So this means that A is negative and is between 0 and negative 1. So we have a reflection of the cat, and then it is also compressed. C represents vertical translation or vertical shift. When C is greater than 0, there is a horizontal translation, absolute value of C units up. So if C is positive, then the cat is going to move up. When C is less than 0, which means C is negative, then there is a horizontal translation, absolute value of C units down. So for example, if C is negative 4, we would say that there is a horizontal translation of 4 units down. We do not say that there is a horizontal translation of negative 4 units down. If we say there's negative 4 units down, we're actually saying 4 units up. Okay, so negative makes it positive. So it's just complicating things. So we use the absolute value to make things easier. We have just finished looking at how to use mapping notation to transform every single point in the original picture to a new image picture. Now we want to look at a bigger picture of how curves or lines are being transformed. So we'll need function notation to describe the bigger picture, not using mapping notation to describe individual points. So in function notation, we have g of x equals to a multiplied by f at, open the square bracket, of 1 over k multiplied by open round brackets, of x minus d, closing the round brackets, closing the square brackets, and then plus c. A, k, d, and c, they have the same meaning as what we saw in the previous slides. So they are the same variables as when we use the mapping notation. However, you would notice that for the x-coordinate, okay, look at the x-coordinate in the mapping notation and look at how x is described in the function notation. They look different. So in the mapping notation, x is supposed to be multiplied by k before adding to d. In the function notation, x is subtracted by d first before divided by k. So we are actually performing the opposite, okay, of what we see in the mapping notation in terms of the order of operation. So in the mapping notation, we multiply by k. In the function notation, we divide by k. In the mapping notation, we add d. In the function notation, we subtract d. It is important for us to remember that the function notation is written differently than the mapping notation. So you have to remember that when you're using function notation, it's 1 over k times bracket x minus d close bracket. Okay, we cannot use kx plus d in the function notation, so you have to remember that. The difference between the mapping notation and function notation is because of the mapping notation describes points and the function notation describes relations. So with that note, you will notice that some textbooks use a different formula to describe the general function notation. So instead the one that I showed you on the previous slide, they would use g of x equals to a multiplied by f at, open square bracket, k, open round bracket, x minus d, close round bracket, close square bracket, plus c for the general function notation. Now in this case, when we describe the horizontal stretch of compression, we need to use 1 over k. So if we're multiplying it in the function notation, when we describe it using the mapping notation, it is still the opposite operation. Opposite of multiplication is division, so we use 1 over k. So here is the mapping notation. So the d part doesn't change. Only the k is sometimes written differently in other textbooks or websites that you see. Now, third note. Now you need to remember that the function notation only describes how a function transforms. When you read the general function notation, it doesn't tell us which function is actually being used. We don't know if we have a straight line, if we have a curve, or if we have a circle, or if we have something else. We don't know. Okay, so the function notation is very, very general. Once we are given the actual equations of the original function, then we can apply the function notation to come up with the equation of the image function. So more information is needed when we use the function notation. In function notation, we describe how to transform an original function to an image function. So using the symbols, the general function is g at x equals to a multiplied by f at, open square bracket, 1 over k, open round bracket, x minus d, close round bracket, close square bracket, and then plus c. When we study specific functions, sometimes we don't have to use all the letters or all the variables in there. For linear functions, sometimes we can just use, for example, n at x equals to a times f at x plus c. For quadratic functions, we can use n at x equals to a times f at bracket x minus d close bracket plus c. For square root functions, we can use p at x equals to a at f at square bracket 1 over k, round bracket, x minus d, close round bracket, close square bracket, plus c. So this one doesn't really change from the general function. For reciprocal functions, we can use q at x equals to a times f at, open bracket, x minus d, close bracket, plus c. So some functions, we don't have to use k. And for the linear function, we don't have to use d either. Okay, so actual equations. So let's look at what happens with these actual equations when we transform. So for the linear equation, f of x is x. Okay, so that is the form for the function. Now for g of x, okay, the actual equation looks like function notation, but you can see that the f is missing. Okay, I'm not describing how g of x is obtained from f of x anymore. I'm just saying what the actual equation of g of x is. So g of x equals to a multiplied by open square bracket 1 over k open round bracket x minus d close round bracket close square bracket and then plus c. And then we can start simplifying. So we multiply 1 over k to what's inside the bracket. We apply the distributive property to have 1 over kx subtract 1 over k times d inside the square brackets. And then we expand further to have a over k times x minus a times d over k, and then we add c at the end. Next, we want to collect like terms so that the x terms are together and the constant terms are together. So to make it easier to read, I just add these extra brackets to help everyone to see it clearly. Now, let a subscript 2 equals to a over k and c subscript 2 equals to c subtract ad over k. If I substitute these into g of x, then I get g of x equals to a subscript 2 times x plus c subscript 2. And then we can compare this with the slope y-intercept form, y equals to mx plus b. As you can see, m is a subscript 2 and b is c subscript 2. So it means the slope is a subscript 2 and the y-intercept is c subscript 2. Let's look at quadratic functions. Okay, the base function of the quadratic function is f of x equals to x squared. That's the simplest one we can have. So when we transform this base function to obtain a new function, the new function would be written as g of x equals to a multiplied by open square bracket 1 over k open round bracket x subtract d close round bracket close square bracket and then square that before adding c. So reminder, once again, this is not function notation because f is not there anywhere. This is the actual equation for g of x. So we're going to simplify it just like how we simplified the linear function before. So first, I can square 1 over k and I can square x minus d separately. And then I can combine a with 1 over k squared, and we have a over k squared. And then c as a constant is added at the back. Now, let's separate everything clearly. Okay, so I put a over k squared in brackets to tell you that I want to look at it as one item. And I want to let a subscript 2 to equal a over k squared. So when I rewrite my g of x, it will look like this. G of x equals to a subscript 2 multiplied by open bracket x minus d close bracket and then square the bracket plus c. We can compare this with the vertex form of the quadratic function. Y equals to a bracket x minus h close bracket squared and then plus k. So back in grade 10, we learned that a represents the vertical stretch or compression of the quadratic function. So now it's represented by a2. And then h and k, that point is the vertex. So d comma c, that point is the vertex. For the square root function, the base function is f of x equals to the square root of x. then g of x equals to a multiplied by the square root of everything inside is 1 over k multiplied by bracket of x minus d close bracket. And then we add c at the end. This is the actual equation of a transformed square root function starting from the base function f of x equals to square root of x. Now, if I try to rewrite this, I can separate 1 over k from x minus d and write two square root symbols. Okay, I have two radicants here. And I can combine a with the square root of 1 over k. So if I let a subscript 2 equals to a times the square root of 1 over k and rewrite my g of x, I have g of x equals to a subscript 2 times the square root of x minus d and then plus c at the end. If the square root of 1 over k is an irrational number, sometimes we don't want to simplify the equation to a subscript 2 because we don't want to work with decimals. If we want exact value, we would keep g of x equals to a multiplied by the square root of 1 over k times x minus d, close bracket, and then we add c after. The base function for the reciprocal function is f of x equals to 1 over x. G of x equals to a over 1 over k multiplied by bracket x minus d close bracket, and then we add c at the end. So this is what the actual equation looks like for a reciprocal function. Let's simplify it. So if I take g of x and simplify it, then a over 1 over k is going to give me a multiplied by k. And then everything else stays the same. If I let a subscript 2 equals to a times k, then it means I have g of x equal to a subscript 2 over x minus d, and then we add c at the end. Note, what is the meaning of the simplification process? Why did I try to simplify them in the first place? We noticed that for all of the functions that we looked at, it is possible to combine a vertical stretch or compression with a horizontal stretch or compression within the equation, and then we can produce a different vertical stretch or compression. So the k can disappear, okay, after the simplifying, and we get a new a at the end. This characteristic just happens to be true because we have these specific 4 types of functions. Later in the course, we are going to study a type of function where we cannot combine the vertical and horizontal stretch or compression together.